the famous speakers for organizing such a wonderful workshop and for the invitation and the speak here. Today, we already heard about reversibility, the irreversibility of the time transformations at this conference. On Monday, I guess, in the World Talks. And I'd like to say about something similar.
Close the microphone, please.
Close the microphone, all right. So I would like to say about something similar about thermodynamics, and I will tell you about some works that we've done with Michael operators during the last 4 or 5 years. And let's see, first of all, those are the wonderful people I was working with on this subject. I will start to talk with some motivation and background. I'm pretty sure that for most of you it's going to be familiar, but it's going to be good for the PhD students, let's say, and just to refresh. And then I will get to some results that we got on the incoherent thermodynamics. Of course, I will define what we mean by incoherent here. And then some more recent results on coherent thermodynamics. All right, so motivation. Question that we're going to ask usually in thermodynamics is, what can we say about the dynamics about solving equations? Like, what can you say, really? And for closed system, this is, you can answer like, well, there's conservation laws, right? So if you have an oscillator, a classical oscillator, and you tell me it's a closed system and you specify its position and momentum, you don't have to exactly solve the equations of motion and to be sure that at any given time in the future, it's going to be restricted to the ellipses in the phase space. And for open systems, it's a little harder, of course, but you also can say things. For example, entropy has to grow. I mean, if you put all the particles in one corner of this room, then you know that later they will rather spread around than the other way around. There is some direction all the time. And what quantum thermodynamics tries to do is to use minimal assumptions of the quantum theory to kind of put constraints on the evolutions of systems interacting with our thermal environment. And some other slide to contrast with the standard open dynamics approach compared to what the quantum thermodynamics community is trying to do is here you have a qubit system, a split level system that is interacting with a single bosonic field. So it's a James Hamilton model. You start somewhere, and this is just the trajectory that goes around and around. You put it for a long time, you plot the trajectory, and this is the exact time evolution for some given model. On the other hand, when you solve the problems in the research thermodynamics, what you rather get is, well, this is your future thermal cone. So you start here, and you're gonna end up somewhere here. You don't specify exact model, you don't specify exact time, but you know that you're gonna be constrained to this subset. So obviously, one is with the other, right? And then, so this is specific models. This is like all models within a big family of models that have some minimal assumptions about interaction with the back and so on. Okay, so what's the thermodynamic setting? I guess you already know, but again, let's remind. We model these thermodynamic transformations by quantum channels known as thermal operations. How do they work? Well, your density matrix, your system is brought together with a path, and then they interact unitarily, but this unitary has to preserve the total energy. So it commutes with the total Hamiltonian, and then you trace away, well, we say P prime, so you don't necessarily throw away all the buff. Maybe you throw away half of the buff and you use the buff as a source of other particles. So you just throw away whatever you want. This way you can change the dimensionality of the systems. Maybe we are graphically in your system, it interacts with the thermal buff, and the buff is prepared to the keep state. And then you can transform it to a different system with a different time and so on, right? Why can you transform it to a different time without different time? This is not important because you cannot do many copies transformations and the dimensionality is going to differ. You can think of this like that. I mean, you start, let's say, with one spin half system with some Hamiltonian, and your path is going to be some big path and also another spin system. And then you throw away this big path and you are left with 2 spin systems. So this is how you can change between system sizes and Hamiltonians. All right, so what kind of questions are started in this framework where there is single total conversion? This is a typical question when you start with some state with system in a state rho, and you ask, does there exist a thermal operation that will transform it to sigma? So this is like, again, all particles in one corner and then the particles around, like one is rho, one is sigma, you can go from rho to sigma, but you can't go to sigma to rho. So we would like to try to characterize all those kind of transformations. The single-shot scenario for one particle, one copy of the system, and then what we're going to be interested in, what we were interested more, is many copies interconversion, meaning, well, you're going to start with n copies of rho. This is the IAD case, that's a simple thing. You have n copies of your system, and the question is, can you transform it to some other number n, let's call it Rn of the state sigma? And the question is like, how large R can be made? So again, a simple example is, let's say you start with, your bath is 200 Kelvin, you start with 10 particles, 210 Kelvin, and you ask how many particles I can get at the end at, let's say, 190 Kelvin. Can I get also 10, maybe only 9, maybe I can get 15? How do you answer this kind of questions? And you try to find the optimal range, and obviously we allow some error, right? We allow for some error of transformation. And what is known is, well, if you set n to infinity, then you're going to get this kind of graph. Here you have on the y-axis, you have transformation error. Here you get the rate, and you realize that, it's a little bit, it looks like a Hamilton's golden theorem or whatever. It's very closely rated. It's basically below some rate, you can do it with simply with vanishing error, and then there's some critical rate after which you can't do it. I mean, you do it with error 1. And the point that we were interested in is what happens when n is not really infinity. It's large, but not infinity. And then this picture, instead of this heaviside step function, this kind of phase transition, let's say, what you get is rather a smooth signal. Right? So this is the heaviside step function is for n infinity. Then for n large, it's like a smooth signal, and then maybe for a smaller n, you get those ones. And there are the different deviation regimes, let's say. I mean, if you just go a little bit around the critical rate, let's say 1 over square root of n to the left or right, then you're gonna get a constant error. If you go, for example, you differ by a constant amount, you get to so-called large deviation regime, and then you're gonna get your error exponentially dying with growing n. So we were interested in all those regimes and trying to understand like what's going to happen when you, let's say, transform 10 to 15 states of the system rather than infinity. All right. And why are we interested in this interconversion? Okay, this was mathematically well defined. Where does there exist a quantum channel connecting, blah, blah. But actually, you can really study a lot of standard problems in thermodynamics and information theory, let's say, or rather connection between information theory and thermodynamics using this kind of interconversion problem. For example, you can ask questions like, how much work, you give me some non-equilibrium state, and you give me access to the big bath, and the question is like, how much work can you perform? So again, you have your bath at 20 Celsius, and you give me an ice cube. And you can imagine that, well, while connecting this ice cube to this 20 Celsius, you can heat up, maybe you can connect some heat engine to it, and you can perform some work. And the question is like, how much work can you perform? And this is really nicely, it's going to be really nicely framed in the interconversion scenario. Basically, you start with a system, you bring some ancillary battery system that is in the ground state, and you want to transform this whole thing. This one you can throw away, you don't care about it at the end, but you want to excite the battery to the excited state over some energy gap W. And you want to go from, so it's pure state to pure state, or almost pure to almost pure. So there's no entropy involved, and then you just have like this energetic storage there. And the question is, what's the maximal value? And of course, you can recover like the result that were already predicted well for classical case, let's say, from like the Zillard engine, and that there's something like KT log 2 going on for every bit of information. But you also can do information erasure, like with Landauer principle. You also can connect with how much you can study how much a given non-equilibrium resource allows you to communicate, for example. Right? I mean, without spending any work, how many orthogonal states you can get to, so that how many messages you can encode. So there's a lot of problems that can be really phrased in this interconversion setting. That's why we try to understand it. All right, so let's go to the results in incoherent thermodynamics that we got. Before I say what the results are, I have to define what the incoherent thermodynamics is. So basically, it's kind of a quasi-classical case where your states, your initial state commutes with your initial Hamiltonian, and your final state commutes with your final Hamiltonian. So basically, they are like mixtures of energy eigenstates, and they can be represented instead of a full density matrix, you can actually just represent it by the distributions over energy eigenstates. And that makes things a lot simpler because you just go from density matrices to probability distributions. And this was already studied 10 years ago. Jonathan is here in this paper. They introduced this thing called thermodynamics. And of course, I'm not going to go to the details, but there's a very simple explanation like how to understand thermodynamics. So basically, if you want to know whether you can start with a state with this energy distribution P and using thermal buff, you can transform it to a different one with Q, what you do is the following game. You draw segments that have x length given by the thermal distributions of the ground state, first excited state, and on the y-axis they have the length of the distribution P1, P2, P3. So you do this for your initial state, you do it for your final state, and then having those segments, you basically there's a unique way to construct a concave curve out of it, right? So you take the one with the biggest slope first, then the one with the second slope, the second is this one probably, and then the third one. So you construct one curve concave, the other curve concave, and if the final one is below the initial one, it's an even only if then there exists interaction with the path that will transform it. It's a really nice geometric way of trying to understand whether you can transform some quantum systems one into another using a thermal path. All right. So what was known also already for around 10 years, I think these papers are relatively at the same time appearing, is what's going to happen when you send this n to infinity. I mean, I already showed it on the graph, but you actually find out that the rate, then the optimal rate is given by the ratio of those relative entropies. So this is relative entropy between the initial state and the thermal state, and this is between the final state and the thermal state. And what's the physical interpretation? If you write down this relative entropy, this is an information theoretic quantity, but if you write it down, it's sum over pi log pi over gamma I, and you remember that gamma I is e to minus beta ei over 7. Basically, what you write down, you realize that this is really the free, let me call it non-equilibrium free energy. So this is, U minus Ts, right? The famous free energy expression. So this is expectation of energy minus T times H. Here, H is not Hamiltonian, sorry for, this is the shallow entropy of this distribution. And then this is the difference between, and this is the free energy of the new state. So this is like how much free energy the system contains above the smallest level, which is given by the free energy of the equilibrium state. Cool. So then I think this people in this paper were happy about this because now you have this information theoretic framework where you have some channels and so on, but then you connect and say, oh, okay, so actually it's the free energy that matters. And free energy, just for those of you who don't remember, maybe it's like how much work can a given system thermodynamically perform. Okay, so then we have this rate, and how we get to this asymptotic reversibility. Well, you start with n copies of rho, and then you try to optimally transform it to Rn copies of sigma, where R is this optimal rate. And then you say, okay, now I want to come back, right? So now you have Rn copies of sigma, and you want to go back to the optimal number of copies of rho. So now you have a different rate, rho prime, because now the initial and final state reversed, but because it's just a simple fraction, R times R prime is simply 1. So you can close the cycle, right? And here you get asymptotic reversibility, unlike the case discussed for entanglement on Monday, right? So here in this incoherent setting for thermodynamics, you really see that as you go to infinity, to let's say the thermodynamic limit, the number of particles and go to infinity, you really can close those thermodynamic cycles. You can start somewhere, you go somewhere else, and you come back, and you don't dissipate any free energy. You just go back where you started. Now, okay, no dissipation of free energy in thermodynamic. But now, what happens when you have large but finite energy? Well, you can expand this. You can expand the rate. You can do the asymptotic expansion. You can write that this is equal to the asymptotic rate minus some function that is a function of your initial state, final state, the number n, the keep state, of course, so the temperature, the allowed error, and so on. So we would like to know what this f is. And what you're gonna see in the next slide is that the relevant quantities now is not gonna be the relative entropy, and not only relative entropy, but also relative entropy variance. So basically you treat this log pi over gamma I as a random variable that writes its variance. What's the interpretation? So the first interpretation we had was like, well, we connected to the specific heat capacity. Actually, when your one state is deep state at some different temperature, and then you realize that this is really given by specific heat capacity times the Carnot factor squared. But more recently, we started treating this basically as fluctuations of free energy. Just don't think about free energy now as a number. Think about free energy as a random variable for which the normal free energy, so this relative entropy, is the average, and this is the variance, right? So this is something that is not a well-defined, it's a probabilistic quantity. I mean, it has a distribution, and the relative entropy is its mean, and this is its variance. So then you realize that if we're gonna show the next slide, that this R is smaller than the R infinity, then well, you do this cycle, you do it, then try to do it back, and because both of them are smaller than the asymptotic one, you can't close the cycle, and you're gonna get irreversibility, right? So if you try to do this cycle for finite number of particles, you will dissipate some free energy. So let's see what the result is. Really, what you get is, in the small deviation regime, so when you allow for a constant error epsilon, you get that your rate is your asymptotic rate, and then there is some terms that are smaller than 1 over square root of n, because you do it up to second order asymptotic correction, so there's some terms that die out quicker than 1 over square root of n, and then this is the correction term. Let's see how it behaves. It dies out as 1 over square root of n, so as you go with n to infinity, you recover the standard result. And then what you have here is, this free energy fluctuations divided by the free energy content. And there's a function here that depends on the error epsilon. I'm not going to get exactly to it. Okay, then this function has it depends on both epsilon and something called reversibility parameter nu. I'm going to get to this reversibility later. But for now, what is important for us is that this function behaves, it's an inverse of some cumulative distribution function. And what is important is that in some cases it just behaves like an inverse of Gaussian CDF, and then we understand everything. But sometimes it can, basically the most important thing, the most important thing is that for small errors it is negative, right? So if you really want to get close to your final state, you're gonna get the rate that is gonna be your asymptotic minus something. Okay, for large error, maybe you can even get better rate, but then you are, your error can be like 1/2. So if you want to go small error, you usually get this negative, unless this reversibility parameter is 1. And I will get to this later, because this is a very special case where we call it a resonance condition, and then you realize that even up to second order, you can recover reversibility, but normally you don't. Normally, you have dissipation of free energy. So let's maybe a quick slide for the numerical verification of this second order asymptotic expression. So what we are able to do is, because we know what the conditions are, right? We know that transformation conditions are given by thermal majorization. You can actually do numerics, exact numerics, for some small number of systems. I mean, okay, it's up to 100. Let's remember that those are probability distributions of qubits. We do not simulate 100 qubits, it's 100 bits. And also IID, which makes it relatively simple. So what we have here is, depending on the number of copies n, you start with some state and copies of it, and you try to get to the as much as possible of the state sigma. And you try to find out what the rate is if you, let's say, allow for the error 0.05 here. So the dots are basically what you get from numerics, and then this solid line is our second order expansion. So and then here for some other two states and a different error. So we see that it's a really good agreement, and then we also see that it goes as n goes to infinity, it approaches the asymptotic rate, right? Okay, so that's nice for verification. And then maybe let's just have some physical pictures here to use this work extraction and or work installation or work formation. So now imagine you have a system, n copies of a system, or you say raw, and you allow it to interact with the thermal bath, and the question is like how much you can charge a battery, how much work can you perform? And This is known as the distance work, and then there's something called work of formation. It's very analogous to what we have in the time. Now you basically bring some source of work and you try to drag out of equilibrium from the thermal bath so that you create a non-equilibrium state in a system in a state rho n. And usually, yes, you can imagine those two things are not the same. In the single shot regime, they are completely different. In the asymptotic regime, when you have infinitely many copies, then well, they become equal because you have reversible cycles so that you don't dissipate anything. And then in this large n limit, you realize that, well, you get this work up, right? There's some asymptotic amount of work, and then there's this work up. So the amount of work that you dissipate is really just directly connected to this relative invariance. And this relative invariance is basically important this physical interpretation of fluctuations of free energy. To really have a connection between, well, fluctuations and dissipation, right? So this means that there was it's a typical thing that you usually calculate dissipation rates are known in thermodynamics program and TS now. So yeah, so what we get here in this framework is that you get dissipation of free energy on the thermodynamic data. It's a very simple example with work extraction. All right, so then let's talk about this resource resonance. I already mentioned something about this reversibility parameter being one. So here I okay, maybe this going to go to next because now I want to show some other results, not about the constant error, but actually the so-called moderate deviation regime. And your error is, going not constant, but it's going down exponentially. And then you find out the optimal rate as well. And you realize, okay, you look at this equation, and you're like, okay, so this there will disappear if mu is equal 1. That's very clear from here, right? If 1 over square root of mu is 1, then this 1 minus 1 is 0, and all this whole term disappears. And then you get only the third order and higher term that will contribute to this. So it actually looks at this mu being 1, this correction term, well, for every error, no matter what the error is going to be, this is going to just disappear. And at least up to asymptotics. And that's an interesting scenario because now just recall that this is what this mu equal 1 is. This was the ratio, this was fluctuations of free energy of the initial state divided by the free energy of the initial state. The ratio with the same thing for the final state. So this somehow shows that if the relative fluctuations of free energy fluctuations of the initial state are exactly tuned to the relative free energy fluctuations of the final state, then you will not get those high order corrections and you will recover reversibility up to certain order. So let's have an example here. Again, it's got some numerics involved. Let's have this situation where you have something like a heat engine, you have a hot bath, you have a cold bath, you have a battery system, and your working body starts at the temperature of the cold bath. Now you bring it to the hot bath, it interrumpts, so there is some heat flowing from your hot bath to your system, and the system then performs some work over the battery. And normally, in the normal standard setup, this you let the working body heat up all the way to the temperature of the bath. But let's imagine we stop at some TC prime, right? So that we don't get, this is, let's say, 20, this is 10, and we let it go to 15, let's say, okay? And then we stop, and we ask, like, how much work can you do in this process? And, okay, let's see with the numerics, how, because I want to really show you why we call it resonance. So let's say you have 200 qubits, there's some energy graph E, you get some background temperature of the hot bath, set to 10 E, KB set to 1. And then you try to fix the efficiency of, like, you try to extract 95% of work that a Carnot engine would do, right? And then you see what the error is going to be. And you realize that if the TC and TC prime are like off resonance, you get relatively large error, and then if you tune them to resonance so that the fluctuations of free energy at TC prime are the same as the TC, then you get, orders of magnitude smaller error, and you actually can get to, this 95% of time efficiency. Alternatively, you can also do it the other way around. You can fix the error would be, let's say, 1010 to minus 3, and then you try to see how much work you can extract as a fraction of what the Carnot engine will do. And you also see that when the initial and final states of this TC prime are tuned to resonance, so the free energy fluctuations are tuned to each other, you really get as close to the Carnot efficiency as you get. Okay. Good. So this was about incoherent thermodynamics. Now let's go to coherent thermodynamics. So let's say half coherent. We'll see what I say half coherent in a second. This problem is much harder, and there's been not that much progress for the last few years. And the reason basically is that all the other results that we had is like, okay, you deal with quantum, but then somehow you map the classical problem, and then we know how to solve it. Whereas when you have, great, thank you. And whereas if you do fully coherent and fully quantum, then well, it seems like we lack some tools. But let's look at this scenario that we studied, this simplified scenario, which is not the interconversion. So we don't have initial state rho general and final state sigma general, but now you allow for the initial state rho to be general. It doesn't have to commute with your Hamiltonian and so on to the end state you want. But the final state is going to be the energy eigenstate. It's like the distillation scenario in entanglement when you try to distill as much deltas. So here you will try to distill energy eigenstates. I mean, those are like, they have zero entropy, they just have some energy constant that you can use as a property. So you start with this state entropies of rho, and it has some non-zero free energy, so this n in the relative entropy, and then it has also non-zero free energy fluctuations. So it has some non-zero variance, relative entropy variance. And distillation is like you try to get the eigenstate of the final Hamiltonian. So it's going to have non-zero free energy, but the eigenstate actually of the Hamiltonian have zero fluctuations. I mean, it makes sense, right? It's a fixed energy state. There's no fluctuation there. And the question is, when you try to do this, is there going to be some connection between the fluctuations of the free energy in your initial state and the dissipated process, the free energy dissipated in this process when you try to optimally transform it? And this reminds a little bit of the Einstein-Swarovski relation for Brownian particles or general fluctuation dissipation. So there you have your system in thermal equilibrium, and it has some position fluctuations because basically it's being all the time hit by the small particles in the environment. And then when you try to pull it out of equilibrium, let's say you try to move it, it's going to feel some friction. And the reason for this friction is basically because it's hitting all those small particles running around. So you see that the friction, the dissipatory friction is directly connected to those fluctuations because it has the same source. It's all those thermal particles running around. And people then realize that the fluctuation dissipations are really connected in a linear fashion. And what we do here is a little bit similar in the sense that, okay, we don't start in equilibrium, we start in some state that has some fluctuations, and we want to drag it out of equilibrium, or not out of its original state by changing its state. And the question is like, how much energy, free energy, going to dissipate? So what we found out is, okay, so first of all, we found the optimal error. So delta F is like how much is the difference between initial and target state. And then you find the optimal error. It's given by this ratio of the difference and the free energy fluctuations, and that is the CDF of Gaussian distribution, but that's not that important. The important thing basically is that we find out that the amount of free energy difference between initial and final states, so the dissipated free energy, is really just proportional to it's a linear in a linear fashion to the fluctuations of the original of the initial state. So it's like a reformulation of this classical fluctuation dissipation in the research language. Okay, I will just skip maybe this it's not that important. And the point is, when I said that it's going to be coherent thermodynamics, in this result we were able to prove for initial pure states. Okay, not for general pure states, but pure states that can have coherence. So that was the first step, and more recently we were able to push this result even further. And how did we do this? Well, okay, I'm going to use the qubit as a simple example. So you have a qubit in a coherent state. In coherent meaning that there is a non-zero term in the coherent state in the energy phases. And when you take n copies of this rho, what you're going to realize when you dephase it afterwards, you're going to have those blocks of fixed energy. So you're going to kill off all the coherent terms outside, but those guys will be there because those are the coherences between the same and then within the same energy eigenspace, and those will not die when you cohere. And then once you dephase like this, you can diagonalize your unit block because diagonalizing just requires an energy preserving unitary. You don't even need a bath for this. And then you are in the coherent state, and then you know how to deal with the problem. So basically, if you dephase at the beginning, so you lose something, but then if you do this, you are back to the classical situation, and you can know how to, okay, it's hard because those things are correlated and so on, but you basically can study and use these thermomodularization conditions. The problem, of course, is in the phase you lose something. But the point is that actually what we realize is you only use log n of free energy, something that stays like log n, because you want to do second order, which stays like square root of n, it's faster, and then we can just, this is higher order 10, it doesn't really matter that much. And the important thing is that what you get is, well, now you get transformation rates for initial state that is completely general and final state that is incoherent. And you get very similar as well, like the equations look almost the same. It's just that this V and D now are quantum, right? So quantum relative entropy and quantum relative entropy variance. You compare it here. Okay, then obviously you can get all the results for extractable or for information rate and so on, so for cost. And maybe, do I still have like, the same one more slide? Yeah, okay, good, thanks. So then the interesting part is you also get this resonance conditions, right? So before we said that there is this resonance when the free energy fluctuations are tuned, but this was only for incoherent states, and you can somehow understand this. But now we have you can extend this to coherent states. So what you have here on the left is a qubit system. So this is a global, and then let's say that the top is the ground state, the bottom is the excited state. Here is the thermal state. Here is your target state that you want to get to, and you consider a family of initial states, all those around this time. And what is being plotted here is this relative free energy fluctuation, so V divided by D for different states. And obviously, then the reversibility parameter is a ratio. So you take a point here, divide by the value here, and you get some number. And when you get 1, you're gonna get reversibility. So you can really then plot the optimal error when you try to transform it with the asymptotic rate, and you realize that when you go along this line here, you're going along this line is exactly going along this line here. You have situations where the optimal error just dies out. I mean, this is again resonance, but now in the coherent scenario, you can actually see that it can happen even for the, it's not a single resonance like before. It can happen for many different values of coherence. All right, so let's see for the output what are some open problems. First, to extend the finite size analysis to other research theories, like asymmetry, convexity, maybe magic, like if you want to see, like, whether you also gonna get dissipation in the beyond the asymptotic field, like wherever you have reversibility, maybe you want to look like, oh, what happens if I actually have like 20 magic states, not infinity many. And then it'd be really interesting to try to use this resonance phenomenon in some experimental setup. Like we really see that there is some setting where you can avoid dissipating free energy. That would be really cool if you could go from this a little bit more abstract framework to actually in some experimental organization. Of course, trying to generalize to include target states with coherence, that would be, solving fully quantum thermodynamics. Look for resonance in any other information theoretic protocols. Like, we already know that, for example, pure state entanglement, you also have this phenomenon. If you have entangled state initial, not maximally entangled, but like some entangled state initial and some entangled state final, sometimes they are tuned such that you can do this without dissipation, without losing entropy of entanglement. And then finally, I think this fluctuation dissipation theorem that we have here, actually, because we formulated in research theoretic language, now this thermodynamic concept could be brought to any other research theory. I think that this fluctuation dissipation thing is not thermodynamic. It's more like a resource thing. It's so you have some things like fluctuations of your resource or an average resource content, and you could potentially have a fluctuation dissipation theorem for general resources. And with that, thank you very much.
Great, what a nice talk, thanks. We have time for 1 or 2 questions. Still early in the morning.
Quick technical question-ish. Is the phasing technical?
Yeah.
Like, how much dephasing? Is it like a lot, or is it like a bit?
Oh, it's full phasing.
Like complete
phasing.
So you're just killing off the coherence.
You are killing off the coherence between different energy spaces, yes. And the point is that if you do this, you just look log n, you just lose log n. And because we look at orders up to square root of n, you can just ignore this.
And this is true even if there is no energy degeneracies whatsoever in the system, is that the logarithm still the ignorable term? So that's,
If there is energy degeneracies, I mean, okay, if there is energy, I would say, okay, we didn't study the degenerate things, but the quick answer is it's gonna be probably even smaller. Because if you get degenerate things, you don't feel coherence between those.
I mean, if you have no energy degeneracy at all,
Yes, so this is the case with no energy.
so no energy degeneracy is still not an even term, yeah, but.
But the point I guess is that you have many copies.
Yes, many
Across the copies, you're gonna have
Ah,
lots of
I see.
degeneracies.
Right.
You're always gonna get degeneracy.
Yeah, okay, now I follow, yes, I can see the truth.
Further questions over there?
Is your work on the fluctuation dissipation, which is related with data generating? They have this coherent fluctuation relation.
I'm not, no, I don't, well, maybe there is a relation. I mean, that if they both the works have fluctuation and dissipation, there must be some connection, but it's not direct related. I mean, we didn't use this word or this framework.
Jonathan, questions?
You could say anything about like, I guess we're often interested in understanding like finite size effects in some limit, but usually like in terms of like the range of interactions or something like that.
Mhm.
You want to say anything about that?
Yeah, so when we say range of interaction, to mean basically that at the given time, let's say only small numbers of particles interact because the interaction dies out farther, right? Or yeah, well, I mean, you could potentially, right? Because I mean, the simplest thing would be like try to model. Let's say you have your because here when you take your n systems and you interact with the bath, you do a global thing. You have to globally control all the particles and the interactions with the bath. So if you add some locality, for example, you could do it by hand by saying, oh, at a given time I can only interact with the bath at the interface, let's say 10 particles out of 100, right? I mean, you could put by hand some restrictions on like how many systems can interact, and this is your locality thing. I mean, this is the first thing that comes to my mind, but like, I don't know, maybe there's a better way of doing this.
Thanks. Yeah, really interesting talk. I'm curious, obviously this framework that you developed is very closely related to information battery, so finding the fundamental work cost of enacting a process rhythm that's converting from state to A to B. I imagine that these finite sort of fluctuation relations would also be extendable to that framework to understand the fluctuations in the work cost of enacting some general quantum process. Is it something that can be extended?
Yeah, so you're asking about going from states to channels, right?
Yeah,
precisely. States to channels. I mean, maybe Philip would know better.
Yes. Both on stage.
Well, I mean, the answer is probably yes. I never did any work in this domain with channels, with thermodynamic channels.
So
But I
this
guess
something that's not yet.
yes. I mean, if you want to work with it, please go.
Right. Sounds good.
Yeah, I think that's a great open problem. And I suggest we move any further questions to the coffee break and thank Kamil again for the wonderful talk.